Hello everybody! Today I will show you how the so-called limit game can help you to develop a deeper understanding of the limit concept, leading to the epsilon-delta definition of limits. Here's an intuitive definition of limits. Limits are usually interesting for functions f at values a, where f is not defined. In other words, a is usually not in the domain of the function f. Since we don't have f of a, we may at least want to tell how f behaves around a. Often the values f of x will get eventually closer and closer to a value L if x gets closer and closer to a but remains distinct from it. Then we say that the limit of f as x approaches a equals L and write it in this form. Note that eventually closer and closer allows that values turn away from L for some time even as x approaches a further, but eventually they will get as close to L as one desires. The limit concept makes also sense if f is defined for a, then f of a cannot be used at all when trying to find the limit of f of x as x approaches a. If f is continuous at a, which is kind of the norm, then the limit equals f of a, but the limit could be really anything or not existing. Does the explanation make sense to you? Totally satisfied? Okay, then thanks for listening. But if it sounds a little fuzzy to you, you may want to stay here, where I will try to lead you a little closer to the epsilon-delta definition of limits, which sets this concept really on a sound basis. The limit game is a game that can be played in order to establish whether a claim about a limit is true or not. It is played by two players, the claimer and the doubter. The claimer claims that the limit of a function f as x approaches a value a approaches a value L. As a formula, the claim is the limit of f of x as x approaches a equals L. In words, the claim is if x gets close to a, f of x gets close to L. The doubter doubts it. How do we find out who is right? We need to make precise what close to a and close to L mean. Is 1.1 close enough to 1? But note the different interests. If the claimer would be allowed to decide what close to L means, wouldn't he or she try to be very lenient here? For this reason, not the claimer but the doubter must determine what close to L would be. This is the first step of the game. The doubter gives a number epsilon greater than 0, which is his or her tolerance for L. Every number whose distance to L is at most epsilon is considered to be close to L. In other words, f of x is close to L if the absolute value of the difference f of x minus L is less than epsilon. The tougher the doubter, the smaller the epsilon. Now is the claimer's turn. The claimer submits a number delta greater than 0, which is the tolerance for a. Every number whose distance to a is at most delta is considered to be close to a. In other words, x is close to a if the absolute value of x minus a is less than delta. Note that the claimer hears the epsilon before having to decide on delta. No delta fits every epsilon. Smaller epsilons usually require smaller deltas. Then the moves are over and the referees decide who has won. They do this by graphing f in a coordinate system window with x values between a minus delta and a plus delta and y values between L minus epsilon and L plus epsilon. If the claim is true, then for all x not equal to a, close to a, f of x must be close to L. Then for all x not equal to a between a minus delta and a plus delta, f of x must lie between L minus epsilon and L plus epsilon, or in other words, the graph would enter the window from left, cross the field without touching upper and lower boundary, and leave to the right, with the possible exception of f of a. If this is the case, the claimer wins, otherwise the doubter wins. If no graphing device is available, we could play a three-step version of the game. In this third step, the doubter would have to point to a violation, tell an x value close to a with f of x not close to L. So step number 3. The doubter gives a number x not equal to a, close to a, an x where 0 is less than absolute value of x minus a, which is less than delta. Then the referees would simply check whether the absolute value of f of x minus L is less than epsilon. If yes, the claimer wins, otherwise the doubter wins. Is the winner always right? No, against the weak player making silly moves you can win even if you're not correct. But if both players play very well, the winner is right. Let's do an example. The claimer claims that the limit of square root of x minus 1 divided by x minus 1 as x approaches 1 would be 1/2. Let's assume the adapter throws epsilon equals 0.1 on the desk. What delta should the claimer use? Delta equals 1 is not sufficiently small, as can be seen in this window here. The graph does not enter from left. However, delta equals 0.1 works. We get this window, which is working. Would the claimer also be able to return adapters smaller epsilon equals 0.01? Now delta equals 0.1 would no longer be sufficient. We would get this window here, again a violation. But delta equals 0.01 would work, as can be seen here. So, 2 attempts of the adapter, but in both cases the claimer can win, so the claim seems to be true. There are positions in chess where checkmate can be forced in a few moves. In that case, the players could stop playing as long as one player can convince the other about the analysis of the forced mate. In the limit game, if the claimer is right, he or she could try to convince the adapter that the case is lost, even before the adapter's first move. For instance, by providing an expression in epsilon, delta equals delta of epsilon, such that for every possible epsilon, the choice of delta of epsilon would win. If this can be done, we have a proof. If such a proof is known to both players, there is no point in playing. Let us show that in our example above, the adapter always wins if he or she chooses the same number the adapter used. Let's use a 3-step version. Assume the adapter chooses epsilon and the claimer the same number delta equals epsilon. Next, the adapter chooses a number x with absolute value of 1 minus x between 0 and delta. The key observation here is that the product of 1 minus square root of x and 1 plus square root of x equals 1 minus x. Therefore, the absolute value of 1 minus square root of x equals the absolute value of 1 minus x over 1 plus square root of x, which is equal to the absolute value of 1 minus x over absolute value of 1 plus square root of x. We just split the absolute value into absolute value of numerator and denominator. And this one is less or equal to the absolute value of 1 minus x, since 1 plus square root of x is greater or equal 1. Now, keep in mind that absolute value of 1 minus x is by definition less than delta, which is equal to epsilon. So we have absolute value of 1 minus square root of x is less than epsilon. Now for the same reason, 2 times 1 plus square root of x is greater or equal to 2. So dividing this absolute value of 1 minus square root of x by 2 times 1 plus square root of x makes it just smaller. So we get this expression must be less than epsilon as well. Finally, we show that this expression 1 minus square root of x divided by 2 times 1 plus square root of x is just the difference of our function 1 minus square root of x over 1 minus x and the assumed limit 1/2. We just need a little algebra. We rewrite the numerator of 1 minus square root of x as 2 minus square root of x plus 1 in parentheses. Then we split this expression into 2 ratios, 2 over 2 times 1 plus square root of x and square root of x plus 1 over 2 times 1 plus square root of x. And in the first expression we cancel the 2. In the second expression we cancel the square root of x plus 1. Then in the first expression we raise by 1 minus square root of x. And then we simplify the first expression, the denominator, and we get our function 1 minus square root of x over 1 minus x. And in the second expression we just have the 1/2. Therefore the absolute value of f of x minus 1/2 is just the absolute value of 1 minus square root of x divided by 1 minus x minus 1/2, which has been shown above to be less than epsilon. This implies that any such x chosen by the adapter in the third step cannot be a violation, so the adapter cannot find any violation, so the claimer wins and the statement must be true. This was a relatively easy pattern, delta equals epsilon. Sometimes a more sophisticated rule for the claimer's response is necessary, as can be seen by our last example. The claim is that the limit of the cube root of x as x approaches 0 is equal to 0. What are you saying? This is obvious since the function f of x equals cube root of x is continuous at x equals 0, which implies the limit of this f of x equals f of 0, which is cube root of 0, which is 0. Yes, you're right. But the logic here is kind of backward. Since how do we know that the function is continuous? Mainly since we can show this claim using this epsilon-delta proof. In this example, the claimer should react with delta equals epsilon cubed to any epsilon the adapter has chosen. Note that for epsilon less than 1, this implies that delta is much smaller than epsilon. For instance, for epsilon equals 0.1, we get delta equals 0.001. Assume the adapter chooses x in the third step, such that the distance between x and 0, which is the absolute value of x, is less than delta but greater than 0. Then the absolute value of f of x minus 0, which is absolute value of x cubed minus 0, which is absolute value of x cubed, which is absolute value of x cubed, is less than delta cubed, which is equal to epsilon. So again, no violation x can be found by the adapter and the claimer wins. Looking at the limit game for certain limit claims and proving that the claimer will always win, as we have just done in two examples, really means proving that the limit is as claimed using Cauchy's epsilon-delta definition of the limit. This definition goes as follows. For a function f defined on an open interval around a, but not necessarily at a, the limit of f as x approaches a equals L if for every epsilon greater than 0 there is a delta greater than 0, such that for every x not equal to a, but with distance to a at most delta, we have absolute value of f of x minus L less than epsilon. This definition used by the French mathematician Cauchy around 1820, about 160 years after the invention of calculus, since when limits have been used regularly, puts the limit concept on solid ground. Thanks for listening.